This is chapter 20, part 1, electric potential. This is an extremely important concept in electricity because all of the electricity that we care about really in life is due to charges that are moving, and specifically charges that move in wires in our house that power our lights and our appliances. Um, all of the electricity that we use is based on charges that are moving or a current. But nothing can cause the current if there isn't a potential difference, as we're going to learn. And a potential difference is really just the same as a voltage. So think of it as like if you have water that's going down a slide, it's a difference in height from the beginning of the water's flow to the end of its flow. That difference in height is what makes it flow. The flow itself is all the water molecules that make up the flow. Okay, so this is analogous to voltage and current, and voltage really is what drives current. And voltage is the same as electric potential, sometimes called potential for short. And so this is a very fundamental concept in electricity, and we're going to learn exactly what potential is, and we'll understand what effects it has. Now, this first image here is a diagram of an ingenious experiment called the Millikan oil drop experiment that was used to find the charge of a single electron. Let's find out more about that experiment right now.
Millikan's oil drop experiment. British physicist J.J. Thomson had measured the ratio of electrical charge to the mass of an electron using a cathode ray tube in 1897. Later, R.A. Millikan looked to determine the charge on the electrons. The famous method that he devised between 1906 and 1914 to measure the charge E of an electron is known as the Millikan's oil drop experiment. Using this method, he calculated that the charge on an electron was about 1.6 times 10 power negative 19 coulombs. In the Millikan's oil drop method, an atomizer produces oil droplets in the form of mist, which are sent through a plate of electrical condenser. There are different forces which act on the oil drop, including gravitational, electrostatic force due to electric field, and viscous drag force. The rate at which these drops fall were measured by observing them through a micrometer eyepiece of a telescope. X-rays were passed through the chamber to ionize the air inside. On colliding with gaseous ions, these oil droplets acquire charge. The rate at which these droplets fall can be controlled by changing the strength of applied voltage to the plate. With this experiment, he observed that the magnitude of electrical charge Q on the droplets is always a multiple of electrical charge E. That is, Q is equal to NE, where N is equal to 1, 2, 3, and so on.
And the value that Millikan was able to find for E was negative 1.60 times 10 to the negative 19th coulombs. He won the Nobel Prize for Physics for his oil drop experiment. But who came up with the term electrical charge in the first place? Well, you might be surprised to find out that we owe that term to Benjamin Franklin.
In his own time, he was known to his countrymen as the wisest and the most worldly man the young colonies could offer. In England and France, he was a legendary and wildly popular figure. Today, we think of him as a statesman who dabbled in science. He was, in fact, a serious and very important player in the history of science. And by far, his most important scientific work had to do with electricity. In fact, when Franklin tried to cook a turkey by electrocution, he almost managed to electrocute himself. In his own words, Franklin described the dangers of electricity. It seemed a universal blow throughout the body, followed by a violent, quick trembling in the trunk, a swelling raised on my hand. My arms and back of my neck felt somewhat numb. My breastbone was sore for a week. Obviously, Franklin had discovered how not to conduct electrical experiments. For the record, however, this error was as rare as the man himself. After all, he was the first to publish a theory of electric charge and electric force. The details would be worked out later. 100 years before Faraday discovered the electric field, Franklin saw it as the electric atmosphere. In his theory, the atmosphere arose from a fluid, an electric fluid, that permeates every object on Earth. Everything, in turn, was a sponge of sorts, which might soak up the electric fluid. Franklin said that when an object soaks up too much fluid, it's positively charged with electric fluid. But if an object doesn't have enough electric fluid, then it's negatively charged. He said that positively charged objects and negatively charged objects attract each other. But two objects that are both positively charged repel each other. Franklin's terms, positive charge and negative charge, are still in use. But even that wasn't the extent of Franklin's fame. He was also recognized as an inventor for a number of good reasons: the lightning rod and the glass harmonica, the rocking chair, the Franklin stove, and even daylight savings time. Another of his inventions, bifocals, would eventually become his trademark. Franklin was also relentlessly optimistic. Throughout his life, he saw everything as a wonderful game. A serious game, to be sure, but also a challenge of limitless possibility. Today, what Franklin saw as the electric atmosphere is seen in modern terms as the electric field. An electric field is present around any object that carries a net electric charge. Of course, if an object's positive charge and negative charge are balanced, the object is electrically neutral, and it produces virtually no electric field far away.
So far we've learned about electric forces and fields. And now I'd like to introduce you to a concept called the electric potential. But I think it's easiest if we first start with something you already know, which is gravitational potential energy in a gravitational field. And so let's do a quick review of that. Let's suppose we have a box. Think of it as a heavy box at point A, just sitting on the ground. And there is a point B above the ground. And so we're going to talk about what happens if we do work on the box by lifting it. If we do work on the box by lifting it from A to B, we are increasing its potential energy. Remember that all work is a change in energy of any kind. And so if we increase this box's potential energy by lifting it, we are doing work on the box. All right, now let's see what that would look like. So we lift the box from A to B, and we're doing work on the box, exercising a certain force over a certain distance, because work is always force times distance. So we lift the box from A to B, we're doing work, which means we're increasing the box's potential energy. All right, and if we increase the box's potential energy, then we've brought it from a low energy state to a high energy state. If we go from B to A, it's just that happens naturally. Things naturally fall from B to A, but they take work to move from A to B. So we could say that A to B requires work, whereas B to A is just natural. It happens naturally. Things naturally go from a high energy state to a low energy state, but they require work to go from a low energy state to a high energy state. So let's think of A to B as uphill, B to A as downhill. All right, so let's lift the box from A to B again. It falls from B to A. And if we lift the box from A to B, we've done work, we've made it go uphill, and then if it falls from B down to A, it's gone downhill. All right, so all that is pretty much review. Now, we have a high potential energy at point B and a low potential energy at point A. And just be patient if this is easy for you, because it actually helps to see things you know first before looking at new things. All right, so if we go from A to B, we're going from low PE to high PE. And we're at that high PE state at B. Whereas if we're at A, we're at the low PE state. All right, so if something falls, it goes from a high PE state to a low PE state. And that, of course, as you know from your observations, happens naturally. It takes work, however, to go opposite gravity from A to B. So the thing to remember in all of this is that moving masses in fields, in this case gravitational, causes changes in energy. If you move with or against a gravitational field, you're going from low to high or high to low potential energy. Now, a similar thing is true in electric fields. Moving charges in electric fields also causes changes in energy. You can move with an electric field or against an electric field, depending on what the sign of the charge is. And so that's really what electric potential is. It refers to changes in energy state when you move charges in electrical fields. Now, before we define electric potential, let's continue with our analogy of the gravitational field, because that's going to help us understand electric potential. Suppose you're riding on a roller coaster, and everyone's familiar with that anxious feeling you get as you're going up the hill, click, 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 and you know what's coming, because when you get to the top of that hill, there's going to be a massive drop, and your stomach will go up into your head, and if you've recently had a meal, you risk losing it. Sorry, I don't mean to gross you out, but you know the feeling of a roller coaster. Now, as you're going up that hill and you're hearing the click, 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 expecting the drop, what's happening to you is that the roller coaster chain and motor is doing work on you and everyone with you in those cars. And it's increasing your potential energy state. And so without you knowing it or thinking about it in those terms, when you ride on a roller coaster, the ups and downs indicate changes in energy state. When you're going up, your potential energy is increasing. And when you go down, your kinetic energy increases, but as it does, your potential energy decreases. Okay, so this again is an analogy that's going to help us to understand the motion of charges in electric fields. All right, now let's suppose we have a negative charge at the center and we have a positive test charge. And the question is, if we're going from A to B, is that uphill, or is uphill going from B to A? All right, keeping in mind that these are unlike charges, what do you think the answer is? If I go from A to B, would that be like going uphill in the gravitational analogy? Or is going from B to A like going uphill in the gravitational analogy? All right, well, you can clearly see that since positive and negatives attract, the positive wants to go towards the negative charge, and therefore moving the charge from B to A would be equivalent to going uphill. And that means that point A is the point of high potential energy, and point B is the point of low potential energy. So the point of all of this is to show you that the movement of a positive test charge within an electric field is accompanied by changes in potential energy, just like moving masses in a gravitational field. And remember that by definition, work, if an external agent is moving a charge within an electric field, work is changing the energy state of the thing worked on. So if you move a charge against the electric field in a way it doesn't want to go, you're increasing its potential energy. And if you move a charge towards where it wants to go, with an electric field, you're decreasing its potential energy. Now, gravitational potential energy is something that we're already familiar with, but let's just do a quick review on it. So PEG, or gravitational potential energy, equals mgh. If we define gravitational potential as the gravitational potential energy per unit of mass, we would have gravitational potential equals PEG over m, which is mgh over m, and that's just gh. All right, now you might be saying, hold on a second, we never learned about gravitational potential. And that's because it doesn't exist. There is no such thing as gravitational potential as far as what you'll see in your physics book. It's not something anyone talks about. But it could be talked about. It could be defined. Gravitational potential could be defined as simply the gravitational potential energy per unit of mass. And that would give us the quantity GH. Now, the quantity GH is quite common, but it doesn't carry the name in the physics books as gravitational potential. The only reason I'm doing this first is because it's going to help you understand what electrical potential is. All right, so if we define gravitational potential, that is, if there were even such a thing in the physics textbooks that was called gravitational potential, all right, this is how it would be defined. It would be defined as the potential energy per unit of mass, giving us GH. And as you can see, GH depends only on position and doesn't depend on mass. That's the beauty of it. And so a high gravitational potential would correspond to a high H, and a low gravitational potential would correspond to a low H. Analogously, we can define electric potential as the electric potential energy per unit of charge. This is what that definition looks like, written as an equation. V equals PEE over Q0. All right, what does that mean? V is volts. Volts is the unit of electric potential. PEE stands for electrical potential energy. And QO is just charge. Now, when you see QO, usually it refers to a test charge. And so test charges often appear in definitions because it's just a standard way of expressing charge. But really all this comes down to is that voltage, or volts, equals electrical potential energy divided by charge. And that is, as said earlier, quite analogous to dividing gravitational potential energy, mgh, by m. The unit of electric potential is the joule per coulomb, and that is defined as a volt. A joule per coulomb is 1 volt, such that 1 volt equals 1 joule divided by 1 coulomb. A volt is the basic unit of electric potential, which is sometimes called voltage. And sometimes voltage refers to potential difference, as we'll talk about later. Now, voltage, or the volt, is named after Alessandro Volta, who invented the electric battery. And Alessandro Volta was an Italian physicist, and in 1800 he came up with the first voltaic battery. And of course, voltaic is named after him too. But his first battery consisted of wine goblets filled with salt water, in which he had electrodes placed and created a certain voltage consisting of the difference in potential between the cathode and the anode. And so it's kind of neat that the first battery was really just a series of wine glasses filled with salt water. And eventually Volta developed another voltaic pile, which consisted of zinc and copper discs alternated with cardboard soaked in salt water and later in sulfuric acid. But it's the same basic principle of a cathode, an anode, and an electrolyte, or a conducting liquid between the two. All right, let's go back to our analogy of mechanical and electrical energy. And now we're still comparing the electric field to the gravitational field. Suppose we have two masses, one's little m, the other one's 2m. So one mass is twice as large as the other. Well, if these are rocks, for example, then the two rocks are at the same height, but the larger one clearly has more potential energy. Because if gravitational potential energy is mgh, well, if m is bigger, then the potential energy is bigger. Now, if we have an electric field, let's say we have this electric field with a charge of plus q and another charge of plus 2q, well, we can see that these positive charges want to go away from the positive side and towards the negative side. That's how they naturally want to go. And so having the positive charges held a certain distance away from the negative where they want to go is analogous to holding two weights a certain height above the floor, because the two weights want to fall. In the same way, these two charges want to go right. So these two charges have the same electric potential, but the larger one has more electric PE. Okay, so even though they're at the same position or the same height, if you like that analogy, the potential energy is different because there's more potential energy associated with the larger charge. So extending the analogy, just as height refers to the position of masses in a gravitational field, potential, electric potential, refers to the position or location of charges within an electric field. All right, and just as with falling objects, objects want to fall towards the ground. So likewise with charged objects, charges want to move with the electric field in the direction of the electric field, which is always towards the unlike charge. So a positive charge wants to move towards the negatively charged plate. A negative charge would want to move towards the positively charged plate. But the distance involved, or the position of the charge within the field, is what we call potential, and it's quite analogous to the position or height of masses in a gravitational field. Why is potential important? Well, this is a fundamental question, because if it weren't important, there'd be no need to study it. All the electricity that really matters to us consists of the flow of charged particles, usually electrons, from a point of high potential energy to a point of low potential energy. All right, so this is what powers all electronics. Your computer, your iPod, your iPhone, your iPad, whatever you use, right? Your washer, your dryer, your, I don't know, your electric clock or your alarm clock that you wake up with in the morning. You know, your radio, everything, all these different electrical and electronic devices that we use, they all depend on the movement of charges from points of high potential energy to points of low potential energy. That is what makes electricity work, all right? And so that's why it's important to study potential. This drop in potential energy goes hand in hand with a positive or negative change in electric potential. This change is called an electric potential difference. Electric potential difference is closely related to electric potential. The electric potential difference is literally a difference in electric potential between 2 points in an electric field. And continuing the height and gravitational field analogy, think of it this way. Suppose you have a rock 5 feet above the ground, and another rock 10 feet above the ground. Well, let's suppose that the rock falls from the 10-foot elevation to the 5-foot elevation. Let's say there's a shelf there at the 5-foot elevation. Well, if the rock falls from a 10-foot elevation to a 5-foot elevation, it's really only fallen 5 feet. 5 feet, because what matters is the difference between the 10-foot position and the 5-foot position. Okay, if you fall from the 30th story of a building to the 20th story of a building, you've fallen through 10 stories, because what's important is the difference between the starting point and the ending point. Okay, so just as in the height of falling objects, what really matters is the difference between starting height and finishing height. The same is true with electric potential. All that really matters for moving charges is the potential at which they started and the potential at which they finish, and the difference between the two is called the potential difference. Okay, so let's suppose we have a big negative charge and we have a small positive test charge, and we want to see what the difference in potential is between point A and point B. All right, so let's suppose that we're just given, or we calculate based on other givens, the fact that at point A, the potential is going to be 35 volts. And so that's the potential at point A for this positive test charge that wants to move towards the negative source charge. All right, now the potential at B, let's say that that's 15 volts. Well, the potential difference, or the difference in voltage, is 35 volts minus 15 volts, and that is 20 volts. Okay, so let's say that if this charge, this positive test charge, falls from A to B, because it naturally wants to go from A to B, well, there's going to be a corresponding drop in potential energy and a corresponding drop in potential. It goes from 35 volts to 15 volts. And what matters then is the difference in potential between the 2 points. And that difference, or that electric potential difference, is 20 volts. And so we could, in common terms, say that the voltage of this difference between A and B is 20. Technically, it's a potential difference or voltage of negative 20 volts, not 20. But voltages are often expressed as positives for convenience. Now, when you're doing calculations, just do as you always do with deltas. Do final minus initial and use the sign that it should be. And so you can use the negative if it should be negative. But just realize that when voltages are expressed in common terms, they are given as positives. All right, so let's look at this 9-volt battery. Let's suppose we hook the battery up to a light bulb, and we connect the light bulb with wires to the negative terminal and the positive terminal. The electrons will flow away from the negative terminal because the electrons at the negative terminal are at a higher potential energy state than they are at the positive terminal. And so that difference in potential energy states, which is also reflected in a difference in potential, is what drives the flow of electrons. So going back to our roller coaster example, let's suppose we're talking about the difference between 30 feet up and 10 feet up. Well, that is a falling distance of 20 feet. And so what really matters is the difference between starting point and ending point. And the same is true with batteries. What matters is the difference between the starting potential and the ending potential. That's the electric potential difference. And that's exactly what we're referring to when we talk about a battery's voltage. And voltage is what drives a battery to produce current. We'll talk about current in the next chapter, but if a battery had no voltage, it would produce no current. Voltage is essential. Now, electric potential difference is defined as delta V equals delta PEE over QO. Now, if you look at that first part of this definition, we can clearly see how it relates to electric potential. Because if electric potential is simply V equals PEE over QO, well then delta V equals delta PEE over QO. It makes sense. All right, so this is the formal equation definition of electric potential difference. And that's equivalent to work over QO. And just remember that all work is the transfer of energy. If you work on something like if you work on a rock by lifting it up from the ground to a height of 2 feet, you have increased its potential energy. And that's why delta PEE in joules equals the amount of work in joules, because it's the amount of energy transferred. And the work that we're talking about here, of course, is the work that you do if you move a charge against the field, or the work that a field does when it moves the charge with the field. Electric potential difference, often called potential difference, is what we normally refer to as voltage. Now, electric potential itself can sometimes be referred to as voltage, but in common practice, whenever you hear about voltage, like on a battery, for example, what they're really talking about is potential difference, because it's potential difference that that causes charges to move. This is a Van de Graaff generator, and this girl looks like she's having a great time. I'd like to briefly explain how the Van de Graaff generator works. It's based on the triboelectric series. So the heart of it is really the combination of rollers and belt. So when the belt is in contact with the rollers, there's a little bit of friction, and that's how charge can pass from one substance to another, as we learned in the last chapter. So what we have here is we have a lower roller, which is going to be low on the triboelectric series. So it could be PVC. We have a rubber belt, and rubber is about halfway or midway on the triboelectric series. So it's going to be higher than the low ones, but it's going to be lower than the high ones. And then we have the upper roller, which is high in the triboelectric series. It could be aluminum or nylon. But the point is that as the belt turns, you can see the direction of the turn, right? This one, in this case, it's rotating clockwise. And so you've got the belt in contact with the lower roller first. Let's see what happens. Well, the lower roller is going to want to gain electrons. And if it gains electrons, it's basically sucking them away from the belt. And so then the belt goes up, as you can see, the mouse arrow is going up. The belt's going up with a positive charge because it's lost electrons. And then when that rubber belt touches the upper roller, remember that it's going to touch something that's higher up than rubber on the triboelectric series. Well, now it's going to gain electrons from that substance, and that substance is going to become positive. And then the rubber is now going to have an excess of electrons on the other side as it goes down, and then it repeats the whole process. So this cycle of gaining electrons, giving them up, and giving them up happens over and over again, so that one side of the rubber belt is positive, the other side is negative, depending on what it just touched. If it just touched the lower roller, it'll be positive, and if it just touched the upper roller going around, then it'll be negative. Now the combs, you've got the upper comb, the lower comb. Notice the combs don't actually touch the belt, but they carry charge because the electric field is sharpest at the points. And so when the air ionizes around the rubber belt, those ions can easily charge the points of the combs. And so then the positive charge is transmitted through the comb to the sphere, where all the positive charge tries to get as far away from each other as they can. Basically, think of that as just a deficiency of electrons. And so we have an accumulation of positive charge on the dome, which is usually a hollow sphere. And then we have a collection of negative charge where the lower comb touches, and usually the lower comb will go to a piece of metal that's on the base of the Van de Graaff generator. It's kind of acting as ground. But we can discharge the upper dome by occasionally bringing it in contact with the negatively charged discharge wand, which is also connected to the negative portion of the or the negative charge buildup of the Van de Graaff generator. So that's how it works. In the old days, before modern particle accelerators, this is what people used in order to accelerate charges, because you can build up very high voltages. A Van de Graaff generator can easily build up, upwards of 50,000 volts, but there's not enough current for it to do any damage. Later on, in a future chapter, we're going to learn how voltage and current work together. But for Van de Graaff, you're getting high voltage with pretty low current. Now let's talk about conservation of energy, and we're going to put all of these different kinds of energy together. Just to keep reminding you that conservation of energy is really a fundamental law of the universe, and that's why we keep seeing it turn up over and over again. Now, so far this year, we've learned about linear kinetic energy, which is 1/2 mv squared. We've learned about rotational kinetic energy, 1/2 I omega squared. Gravitational potential energy, which is mgh. Elastic potential energy, which is 1/2 ks squared, and that's, you know, the springs. And electrical PE, which we're learning about in this chapter. So the total energy in a system then would be 1/2 mv squared plus 1/2 I omega squared plus mgh plus 1/2 ks squared plus PEE. All right, so this is really just an application of a concept you already know, and we're simply extending it now to include electrical PE. So let's look at this problem. A test charge moves from point I to point F in a uniform electric field. The particle's mass is 3.6 times 10 to the negative third kilograms, and its charge is positive 6.0 times 10 to the negative third coulombs. The electric potential difference delta V between the 2 points is negative 25 volts. If the test charge starts at rest from point I, what is its speed at point F? All right, a couple things to point out really fast about this problem. First of all a negative voltage means when you're talking about potential difference is that there's a drop in potential. And we can clearly see that here if we look at points I and F. Because if we have a positive charge going from point I, which is close to the positive plate, to point F, which is far from the positive plate, then we have a loss of potential because it's going from a high energy state close to the positive plate and to a low energy state far from the positive plate. All right, so really you'll see potential differences given as both positives or negatives. They're usually given as positives. The only reason it's negative here is because we're going from a high energy state to a low energy state, and so there's an energy loss and a voltage drop. All right, so the other thing to keep in mind as well is that since this is conservation of energy, we need to figure out what energy is involved here, and then we can solve. Now what I'd like you to do is just bear with me for the first few steps. I'm going to walk you through those, and then you'll be able to do the rest on your own. Okay, so let's talk about the first part of the solution. We write down our givens. We know the mass of the particle, the charge, and the voltage, delta V, potential difference. We also know that there is no rotational kinetic energy, at least, you know, we're not given any information about spin of this particle. So we can disregard that. We can disregard elastic potential energy and gravitational potential energy because it's moving horizontally and there's no work with or against gravity. And so the net energy is going to involve only linear kinetic energy and electrical potential energy. So we're going to have KELF plus PEEF equals KELI plus PEEI. The final linear kinetic energy plus the final electrical potential energy equals the initial linear kinetic energy plus the initial electrical potential energy. And so what that's going to come down to is 1/2 mvf squared plus PEEF equals 0 plus PEEI. Now we can't fill in values for PEEF or PEEI yet, but we can rearrange the equation like so. PEEF minus PEEI equals negative 1/2 mvf squared. And by definition, whenever you see a final minus initial, that always means delta. And so we have delta PEE equals negative 1/2 mvf squared. And here, of course, we'll use the fact that delta PEE equals QO times delta V, and that simply comes from the definition of delta V, because the definition of delta V is delta PEE over QO, and so delta PEE equals QO times delta V. All right, at this point, you should be able to do the rest of this problem on your own. Pause the video, go through the steps, and then resume when you have an answer or if you get stuck. All right, going through the rest of the solution. Negative 1/2 mvf squared equals QO delta V. 1/2 mvf squared equals QO negative delta V. We just moved the negative sign. And getting VF by itself leaves us with VF equals square root of 2QO times negative delta V all over M. And now we can do our plugging and chugging. And we fill in our givens like so. Notice that the negative 25 volts becomes a positive because it was negative delta V. And we end up with a final speed of 9.1 meters per second for that particle. Potential difference in a uniform field. All right, it takes work to move an electric charge against a uniform electric field. And we know that already because we've talked about the work that you do if you move a charge against a field. And the field itself does work on the charge if the charge moves with the field. In any case, work, as always, is force times displacement. Now, another symbol for displacement is just distance, and so we can replace the S with D. That doesn't matter, it's just a symbol thing. Same definition of work. And drawing on what we learned from last chapter, which is simply that F equals EQ. And you can quickly find that equation in your last chapter's notes if you need to refer to it. F equals EQ. We replace the F with the EQ, and we end up with delta PEE equals EQD. And for this, we just use the fact that work is always a change in energy. And if you move something from a low energy state to a high energy state, there's a delta PE, and that equals the work. And finally, we can rewrite this equation as delta PE over QO equals ED. And now we can recall an earlier definition that says that delta V is the same as delta PE over QO. And we have this highlighted formula, delta V equals ED. And this is true when we're talking about uniform electric fields, such as the fields that exist between parallel plates. The units of electric field, as we can see from this formula, are newtons per coulomb or volts per meter. All right, the units of electric field from the last chapter were newtons per coulomb. That's nothing new. But here we see that electric field can also be expressed in volts per meter. And they come out actually being completely equivalent. Here's a quick proof that newtons per coulomb is the same as volts per meter. You just replace volts with joules per coulomb, and then a joule is a newton meter, and then that all works out to newtons per coulomb. So volts per meter and newtons per coulomb are interchangeable units of the electric field. Let's look at this problem. Two charged parallel plates are 4.0 centimeters apart. The magnitude of the electric field between the plates is 625 newtons per coulomb. What is the electric potential difference between the plates? What work is required to move an electron from the positive to the negative plate? All right, what you're going to want to do is use the equation you just learned, and you're going to use that in A, and then you're also going to use something you learned a little bit earlier for B. So pause the video, do as much of this as you can on your own, and then resume when you need some help. Okay, so let's walk through the solution. we write down our givens as always, and we also write down what we're trying to find. So let's first figure out our delta V. So delta V equals ED, and that's simply the givens. So we do our plugging and chugging, and we find 25 volts is our delta V for this uniform electric field. Now, delta V equals W over QO, as we learned earlier in the video. And therefore, if I want to find the work, I can use that equation. And I'm going to end up with work being 4.0 times 10 to the negative 18th joules. Now you might look at the sign and wonder why it's not negative. And the only reason for that is if we go quickly back to the sketch, I'm just going to go back and then I'll come forward again. If we quickly go back to the sketch, notice that Q is an electron, and since it has a negative charge, right, it's moving towards the negative plate. Now that takes work from an external force because that's not how Q wants to go. Q wants to stay on the positive side. All right, and so keeping that in mind, we know that positive work is being done because we're forcing the electron on over to the other side. And that's why we're going to express the work as positive 4.0 times 10 to the negative 18th joules. Electric potential of a point charge. In a gravitational field between two objects in space, PEG is force times distance. All right, so imagine you have, I don't know, two asteroids in space. M1 would be asteroid 1, M2 is asteroid 2. Well, there's going to be a force of gravity between them. But there's also a certain potential energy associated with the position of the asteroid, each asteroid, in relation to the other. And that would be expressed as simply force times distance. Okay, notice that we've got force times distance here. If you look at it this way, if you remember from chapter 5, gravitational force is simply expressed as G m1 m2 over r squared. So that's our F. And our distance is simply this r, which separates the two masses, right, the two asteroids. And so we have force times distance, which is the same really as work, and work is the same as a delta PE. And it's similar as well if you think of mgh, because m times g gives you force and h is the distance. In any case, gravitational potential energy, when you're talking about two things floating in space, for example, just two objects in general, is g m1 m2 over r. Now we're going to do something analogous when we talk about electric potential of a point charge, and let's look at that. In the same way, PEE is force times distance. And so we know our electrical force from chapter 15 is expressed using Coulomb's law. And Coulomb's law says that electrical force is K Q1 Q2 over R squared. And the labels don't matter. We're just here calling it Q and QO. It's the same thing, two different charges. So I've circled the electrical force, and it's force times distance, and that's why I have R here, and I end up with something very similar, as you can see, to PEG, and that is K Q QO over R. All right, now at this point, it'll be pretty straightforward to go through the rest of the derivation. V equals PEE over QO by definition. And we replace the PEE with KQQO over R. And we still have the QO in the denominator. And therefore, V equals KQ over R. So we can calculate the potential for any charge. And all we need really is the electrical constant K and the distance from the charge.
Here are the four different situations you can have. And we're going to talk about the difference between electrical potential energy and electrical potential, which, as you can see, depends on what you're looking at, and depends on what combinations of charges you have. So the top two squares are probably easier, more intuitive. The bottom two squares less so. But the way to understand all four of these squares is the KQ over R that we just derived. V equals KQ over R for any point in space. And so what we'll do is we'll consider each one of these four squares by thinking about what point of space we're dealing with. Okay, so let's start with the top two squares that are easiest. If I have a positive test charge, so think of it as a small positive charge in the vicinity of the large positive charge. Well, in this situation, what I have is as I bring that positive test charge closer to the big positive charge, I have a high potential energy situation, because if I were to suddenly let go of that small positive test charge, it would fly off. Okay, the way that it would want to go is away from the charge that repels it. If I would bring this small positive test charge far away from the large charge, well, I can see that's a low potential energy situation. Okay, so that's straightforward. As far as the voltage, remember we're dealing with KQ over R, and the Q in the KQ over R isn't the Q of the test charge, because as we saw on the previous slide, the QO cancels out. The Q that we're dealing with in KQ over R is the large charge that's causing the voltage. Okay, so if I'm at this point in space, you can see the mouse arrow. If I'm at this point in space, or a point in space that's close to the large charge, it's a high voltage situation. Why? Because I have a small r, and since r is in the denominator, the smaller r is, the bigger KQ over r is, or the higher the voltage. And if I have a big R, such as this situation down here, and keeping in mind that Q is that big positive charge, well, a big R in the denominator means a lower magnitude for V, and that's why I have a low voltage situation. Now, in the top right square, I have something similar going on, but now a positive test charge, and I have a negative large charge that's causing the voltage. And so what I have here then is the positive charge wants to go towards the negative charge, and so this region would be low potential energy. Whereas if I pull the positive charge away from where it wants to go, that's a high potential energy situation, similar to or analogous to holding a marker or a weight or anything at a certain height above the ground, if we're using the gravitational potential energy analogy. Now, for the voltage, I'm going to have a low voltage in this situation when I am at a point in space close to the large negative charge. Because now, keep in mind that even though I have a high magnitude, right, I have a negative magnitude, because KQ over R means that Q is going to be negative, and so the whole thing will be negative, and something that's very negative is very low. That's why we're calling it low voltage. Whereas if I pull something away, so let's say I'm at this point in space where the mouse arrow is now. This point in space is far away from that large negative charge. Okay, and so I have a lower magnitude of V, but the reason I call it a high V is because you've got KQ over R being high, but Q being negative, meaning that the voltage at this point in space, where my mouse arrow is less negative than the other point in space that we already did, and less negative means higher. Okay, now let's look at the bottom two squares. Okay, so the bottom two squares, the potential energy part is pretty easy to understand. You know, if the negative test charge is very close to the large negative charge, that's a high potential energy situation. It wants to run away. And then we have a low potential energy situation when the negative test charge is moved farther away from the large negative charge. because, it's already where it wants to be. It's not going to rush off anywhere. Now, why do we call this low voltage in this region of space? Okay, well, in this region of space, it's kind of like what we already did in the top right. KQ over R means that I'm going to have, a pretty high magnitude, but it's going to be a large negative number because Q is negative. And so a large negative number is a low number. Whereas what I have in this region of space, also just like what we did in the top right square, is I have a lower magnitude, but it's a less negative magnitude, right? It's smaller number. The absolute value will be smaller, but it's less negative than it was, and so we would call it a high voltage. And finally, bottom right, similar situation with the electrical potential energy. Low when it's close because it already wants to go there. High when it's far because it wants to rush towards the large positive charge. And then we have high voltage, low voltage. This situation is similar to what we did in the top left square. Okay, because the Q is positive, so we have a high magnitude positive, which means high voltage. And then down here in this region of space, Q is still positive, but I have a low magnitude positive, and so I'd call that low voltage. All right, so these are the four situations, and as you can see, KQ over R is the key to understanding all of them. Keeping in mind, of course, that the Q we're talking about is the large one because the test charge, the QO, was canceled out when we derived KQ over R.
Look at this problem. What is the electric potential at a point 20 centimeters from a positive 10 microcoulomb charge? Pause the video, do this on your own using what you just learned, and resume when you have your answer. So we simply use that equation, V equals KQ over R, and do our plugging and chugging, and we end up with 4.5 times 10 to the 5th volts. Now, the reason that problems involving electric potential are easier than electric field or electric force problems is that if a point is acted on by two or more charges, the electric potential is simply the sum of those potentials. And since electric potential is a scalar, not a vector, you don't have to worry about direction. So remember, scalars have only magnitude. Vectors have both magnitude and direction. So with the electric potential scalars, all you have to worry about is whether it's a positive potential or a negative potential. And if a potential is caused by several charges, all you need to do is add up all the individual contributions from each charge, keeping track of the signs. Now, keeping in mind that electric potential is a scalar and you don't really have to worry about direction as you do with vectors. These kinds of problems are actually easier than the similar problems that we did for electrical force or electrical field, which did involve vectors. Alright, so the problem is find the electric potential at points A and B. Then find the potential difference between the 2 points. Okay, so I'm going to walk you through the geometry part of this problem, and then you'll be able to do the rest on your own. Okay, let's go through the geometry part first. Alright, if you look at point A, you know that A has a certain potential that is being caused by Q1 and Q2, and that's why you need to know the distance from A to Q1 and the distance from A to Q2, and that distance is 60 centimeters. How do we get that? It's the hypotenuse of this right triangle, and I'm right now tracing out the right triangle that I mean. This right triangle here, as you can see, has a hypotenuse of 60 centimeters, which we calculated using the base of 52 centimeters and a height of 30. Okay, so we've got that part of the geometry down. Now we also need to know the distance from B to each charge, Q1 and Q2. And since we can see that we're dealing with an equidistant point, right, 26 on either side, well, if it's 39.7 centimeters on that side, again, simply using the Pythagorean theorem, then it's also 39.7 centimeters on the other side. Okay, so now that that geometry is out of the way, you should be able to do the rest of this on your own. Just remember that to find that potential, you're going to figure out what the potential is that Q1 is contributing to and what the potential is that Q2 is contributing to. You just add those together and you do something similar for B. So pause the video, try this on your own, and resume when you have your answer. All right, so going through the solution, let's write down our givens and what we're trying to find. So when you're writing down your givens, that's also a good moment to do your unit conversions. So microcoulombs is just 10 to the negative 6, so we write that out as 10 to the negative 6 with the 50 and the negative 40. 30 centimeters is just 0.30 meters, etc. So we write our givens, and we're trying to find the potential at A, VA, and the potential at B, VB. So let's calculate the potential at point A. VA equals KQ1 over R1A plus KQ2 over R2A. And so we have just our plugging and chugging step, and that comes out to 9.0 times 10 to the 5th volts. Now let's calculate the potential at point B. So we have VB equals KQ1 over R1B plus KQ2 over R2B. We do our plugging and our chugging, and we get VB equals 2.3 times 10 to the 5th volts. Finally, let's calculate the potential difference between the 2 points. And so all you need to do there is subtract. Now, potential differences or voltages can be given as negatives or positives. Remember, it's just a matter of perspective and what kind of charge you're dealing with. When it doesn't specify, it's always preferable to give it as a positive. And so we're going to do VA minus VB, and that gives us 9.0 times 10 to the 5th minus 2.3 times 10 to the 5th, and that equals 6.7 times 10 to the 5th volts. Here's the class work. Please write these numbers down, which I will post as a worksheet. See you in class.